11.2. Actually, it's not really 11.2. That's what it used to be. Now it's Unit 4, Day 2. Match things up. Ellipses, ovals, if you want to be slang about it. They can have a left-right orientation or an up-and-down orientation. And we'll talk in a minute about what controls, which way they're oriented. Standard form looks a little bit like a circle. It's got a fraction involved in it, though. So let's pause there for a minute. X minus h squared over something plus y minus k squared over something equals 1. So you can see there's a little bit of a circle influence there. In fact, if there wasn't over anything, you'd have a circle of radius 1. And I guess that makes sense because circles and ellipses, their shapes are similar, so their formulas are similar. But not exactly the same. A squared and b squared. A couple things about ellipses. Always positive, so that symbol right there is always a plus sign. If it's a minus sign, it makes a different shape. So it's always a plus sign. And we will do the minus sign later. So ellipses are always plus sign. Always equal to 1. It doesn't mean the radius is 1. It means the radius is sort of underneath each piece. It's like they have different radius in different directions. So the x radius is under x, the y radius is under y, is the easiest way to think of it. The x is always first. Some of these explanations will make more sense when we see the other conic sections because you'll see the differences. Right now, this is kind of the only one we've seen, so it's hard to compare it to anything. But we'll always put the x term first. A is greater than B, so A is always the big one. But A can go with x or y. Okay, so it doesn't always look like that. You can have the A and the B switched. All right, let's do a kind of a generic graph of this. The center would be at HK, just like it is for a circle. That is true of all of the conic sections. They're all going to have an x minus h and a y minus k, and that's always the center. So again, I'm going to do a graph, not really on graph paper, not with any numbers, just so we can get the feel for what it looks like and where these numbers come from. Right. Whatever is under the x is sort of the x radius. Okay, so instead of having one radius over here where we go that many and up and down and left and right, we have an x radius and a y radius. So in the x direction, we're going to go a away on either side. So somewhere out there, doesn't really matter how far. Put a and then put it equal distant on the other side. Again, don't really get hung up on which one's A and which one's B. That doesn't really matter. If it's under X, go that many in X. If it's under Y, go that many in Y. So again, that's why I like to say it's sort of the X radius and the Y radius. It's not technically a radius because it's not the same all the way around, but when it comes to graphing, that's an easy, good way to think of it. So in the Y direction, we'll go B up and down. And we just said that A is always bigger than B, so make sure your up and down distance is less than your left and right distance. graphing purposes, we'd be ready. So just like the circle where you got 4 points, of course the circle is the same radius, up, down, left, right. Here we have a different radius for left versus up, down, but we're ready to sketch in a oval. Hey, that's not a bad oval for my first one. And just like the circles yesterday, I'm not grading on your artwork, but if you just play connect the dots and make a diamond, I will take off. All right, these points on the ends that we found, those are called vertices. The 4 vertices. There's 2 axes. The long one is called the major axis. Major because it's bigger. You want to take a wild guess as to what the shorter one's called? The minor axis. And this, I don't know if this is necessary to write down because you could figure this out. So I'll ask you, look at the picture. How long is the major axis based on the letters that I've got in there? How long is the major axis? 2A. A plus A is 2A. And that makes the minor axis 2B. So I don't think that's something you have to like memorize because you can look at the picture and figure it out. So this you got to know, but this stuff, some of that you can figure out. All right, an ellipse has foci. Again, I don't think you've done ellipses before. So foci are on the major axis. Not on the minor axis, but on the major axis. And they are C away from the center. So we got A, B, and C going on in this picture. C away from the center. How we find C is going to look maybe a little bit strange. C squared equals A squared minus B squared. Okay, that's a little bit weird because you've done A squared plus B squared equals C squared for several years. But this is A squared minus B squared. And you'll end up with a number that's smaller than A. So there's a focus. And equally on the other side is a focus. And those are C away from the center. The good news is, well, I guess first the bad news. For hyperbolas, it's A squared plus B squared. So you got to remember which one's which. The good news is, if you do this one wrong, you end up with vertices that are outside the ellipse. Or excuse me, not vertices, but foci. Foci is plural of focus, so that's sort of the focus of the ellipse. Things need to be focused on the foci. And so if you get this backwards and do A squared plus B squared, and then go C away, you're going to end up outside the ellipse. So you're going to realize, wait a minute, that can't be the focus if it's like outside of the shape. So even though this is a little bit weird and it's opposite of the other one that we're going to do, most people are fine with this, because if you get it backwards, you will immediately recognize that something's not right when you're outside the ellipse. So it's different, but it kind of catches itself when you go to graph it. All right, last thing, and then we'll do an example, and that is eccentricity. Eccentricity. Eccentricity is C over A. And for an ellipse, this is another one of those things that you don't really need to know, but if you know it, it helps you with the graph. The eccentricity for an ellipse is always between 0 and 1. Do you know what eccentric means? Maybe you've heard that word to describe people. Give me a synonym for eccentric. If someone is eccentric, what does that mean? Odd. Odd's a good word. A little bit different. They're eccentric. And it's, I don't know if I guess it has the same root word, but it kind of means the same thing here. The more eccentric you are, the flatter the ellipse. So the further out you go, the more eccentric you are, the closer to 1 you are, the flatter your ellipse. If your eccentricity was equal to 0, you would actually have a circle. So that wouldn't be very eccentric at all. It's just a normal little circle. So it kind of fits with our normal definition of eccentricity. How weird is something? Well, at 0, that's not weird at all. It's just a circle. As we get closer to 1, it gets weirder and weirder. We get this really flat, stretched out ellipse. Very eccentric, odd ellipse. All right, that's a lot of information there. But when it comes to graphing them, the big thing is, if it's under x, go that many in x. If it's under y, go that many in y. The rest you can kind of muddle through if you don't remember it at all. Let's do an example. Example 1 and only 1. Because there's a lot of stuff in this. So this is a really good example. I'll cover it all here. 4x squared plus 9y squared minus 32x minus 90y plus 253 equals 0.
That's pretty easy number.
Yeah, you're welcome. Yeah, weird numbers. Like, what in the world is going on here? Well, kind of like we did yesterday, I have no idea what that ellipse looks like. I can't do anything with that right now. I need to change that into standard form to start to make it look like something I can deal with. So I can't divide through by anything. That 253 is really messing things up. So let's just at least group the x stuff together. And leave a little space again. Group the y stuff together and get that 253 out of the way. Alright, so that's just rearranging. That's hopefully not too big of a deal. Do you remember what we did next?
Complete the square.
Complete the square. Good. Except that to complete the square, we had to have one condition going on that we don't have here.
A equals 1.
Good. A has to equal 1, and I don't have that here. So I can kind of force that, though, if I factor out a 4, and I factor out a 9, now I've got A equals 1. Plus my b over 2 is going to be a lot easier. So most people, they don't forget to do this step because you don't want to do b over 2 is 16 and 16 squared. You don't want to mess with that. B over 2 is 45 and then square 45. So you'll remember to factor out the number that's on the x squared because it just makes life a little bit easier. So let's start in with the b over 2 stuff. b over 2 is negative 4. All right, this is the half it, square it, add it phase of completing the square. So half it, negative 4, square it, I get 16. So be very careful right here. So I want to add 16. That's the normal thing to do. So I wrote down plus 16 on the left-hand side. But I didn't really add 16 to the left-hand side. I wrote plus 16, but what did I really add to the left-hand side? Yeah, 16 times 4, because of that 4 out there. So I wrote plus 16 to make the square thing work, but because of the 4 out front, I really need to add 64 to the other side. And I'll admit, that looks a little bit weird. It's like, wait a minute, I thought you're supposed to add the same thing to both sides, right? That's the rule of algebra in 8th grade or 9th grade. Like, well, I wrote different things, but I really added 64 to both sides because of that 4 out there. And that is a common mistake, is to get into this habit of, a good habit of writing plus 16, except that it wasn't really plus 16 on the left. All right, for the y stuff, b over 2 would be negative 5. So I square it, I get 25. And I got the same issue. I write plus 25 on the left, but I didn't really add 25. What did I add?
220.
Yeah, whatever 9 times 25 is, which is 225. All right, so let's clean up on the left here. So that inside is x minus 4 squared, 4 out front. For the y stuff, it's y minus 5 squared, the 9 is still out front. On the other side, you would have a calculator for this section. 64 plus 225, 289 minus 253, 36. That's a nice thing to end up with there. All right, I'm closer to matching my standard form here. What did we say always has to be on the right-hand side? 1. So what can I do to make the right-hand side equal to 1? Let's divide by 36. We'll fix the left in a minute, but on the right-hand side, if I divide by 36, I'll get 1. And then you start to realize, wait a minute, this problem is rigged. In a good sense, it's rigged. Because 4 over 36 would reduce to 9 in the denominator. 9 over 36 would reduce to 4 in the denominator. And now I've got an ellipse in standard form. So this is one of those, it's like 2 problems in one here. You got the first problem is the algebra to get it looking like an ellipse. The second problem is, okay, now use that to go graph the picture. All right, well, the center will be at 4, 5. Another freehand graph here. Do your best. Again, you've seen the worksheet packet has graphs on it, so you'll be better set for the homework. Let's see. We said A is the bigger one, but I don't really care in terms of who's A and who's B. It's better to just think 9 is under the X, so how many left and right will I go? What's my left-right radius? If 9 is under the x squared term? 3. So A is equal to 3. Again, this will be much easier when you've got your own grid paper to work on. Under the y is 4, so that's 2 squared. So we'll go 2 up and down. And that's enough to sketch in our ellipse. That's not too bad. The things we're going to ask you for are the vertices and the foci. And eccentricity. So we got to find all those things. The vertices we just found, we plotted them, and so it's usually easiest to put them on the graph first and then just read off the graph what they are. Let's see, so we went over 1, 2, 3, 4. Did I go over 5 and up 5? We're just going to have to cancel one of those. I'm supposed to go over 4. So this vertice or these two vertices are over 4 up something. That would be these two. Over 4. The center was up 5, and then we went up and down 2. So this one was at 4, 7, and this one was at 4, 3. I think it's easiest to do the graph first and then grab your vertices from the graph. The left and right vertices, their y-coordinate is at 5. And their x-coordinate started at 4, but then it went left and right 3. So this would be 7, 5 on that side. And we started at 4 and went backwards 3, so that landed at 1, 5. This is a lot easier when you have a nice graph paper to work on. What's left? That's most of the points for this problem, but we also want to find the foci.
You have to write it in that order.
You don't have to write them in any particular order. You can after you graph it, if you can just go around the circle, you can. I usually think of them in pairs, so you can write them together, but it doesn't matter what order you write them in. Good question. C squared equals a squared minus b squared. And here's the only place that it matters that you know which one's a and which one's b, because you got to do the big one minus the little one. So even if you get it backwards over here, it doesn't really matter as long as you go whatever's under x, go in the x direction, whatever's under y, go in the y direction. And when it comes to subtracting, you got to do the big one minus the little one. So c is the square root of 5. That's not the foci, that's just the distance the center is from the foci, or the distance from the foci to the center. So my center was at 4, 5. I already had that written down. But am I going to go left and right for my foci or up and down for my foci? Why left and right? That's the major one. They always go along the big one. So I need to go left and right square root of 5. So what's an easy way to go to say left and right with one symbol, plus or minus? So I'm going to start at 4, that's the x-coordinate, because I'm going left to right, plus or minus square root of 5, and the height is still at 5. Now be careful, because obviously, if they were up and down, then you would add the c to the y-coordinate, not the x-coordinate. All right, now that one problem covered a whole lot. Most of the problems you get are going to be sort of either the first half of this problem, like getting down to the standard form, or they'll be the second half of the problem, taking standard form and doing stuff with it. But just to make one example work for the whole class, we just did one really long one. All right, obviously you have the worksheet packet from yesterday. If you're online, you can print out the whole thing. It's only the second page, or the back of the first page. And how do I say this? Unit 4, worksheet 1, page 2. I mean, it's not hard to figure out. You work until it hits hyperbolas, and then you think, we haven't done hyperbolas. So you stop there. So 1, 2, 3, 4, 5, 6 problems today. It's 8 through 13. So try those, and we'll look at those tomorrow.